Hello guys, uh, this video is about week 8 Hi guys, so this video is about week 8 tutorial entitled load calculation, and we're still on part 1. So in these questions we are going to discuss on how are we going to use the sensible heat ratio, some of them, to design a space, design and condition a space. And we're also going to discuss about the usage of Economizer and how is it going to be used during winter and also during summer. So we are going to use a psychrometric chart in this tutorial. So have your psychrometric chart, both SI and English unit handy, and then we can do this design together, right? So I would like you guys to go to our times page and go directly straight to tutorial section and open the tutorial 8 link. Right, so let's go there now. Alright guys, so as usual, you are looking at our times page, air conditioning and refrigeration engineering, and quickly scroll down to tutorial section. Tutorial section, and then go to week 8, right? Week 8. Now you can go straight to open the answer, and I would like to show you guys that if you opened our tutorial week 8, it is labeled as week 7. So in the past it is during week 7, right? Because that time the test was not done in week 7, right? And I don't bother to change it because what we want is the content. So therefore I will go to my PDF Expert app to do the annotation. Okay, okay guys, so let's the one that I explained just now. So this will be week 8, yeah, in this case. All right, so let's read this question. Number 1, how an economizer to be used an advantage during winter month, and B during summer month, right? Economizer is a device where you can control condition to open the damper of the outside air as it follows these condition, yeah, right? So what happened is there is a damper, motor damper, in this section, also in this section. So an economizer usually can close these two, outdoor air and exhaust air. So air will be circulated inside this space without having any air intake to refresh whatever content that it has within the room, right? That is an economizer. Okay, so usually economizer, the condition will be T1 is less than T4, or the enthalpy at state 1 is less than state 4. This is of course true because our outdoor air and the indoor air usually is different. So usually T1 is less than T4, right? Because T4 is after a room, where a room, this one is a room lah, room, and this condition is hot, right? So state 4 will always be hotter than state 2. So this is the normal condition of an air conditioning system in this case. Alright, now the condition is not given in the question, but the questions are given here. The return air is more or less 75 degrees Fahrenheit, and the phi, or relative humidity, is 50%. So you have here a Q device, which is a heating coil. That means it will inject heat into this system, right? Inject heat into the system, and the room shall be conditioned to be warmer, right? Technically it will be warmer. If this is used during the summer, Q will be taken out from the system, or a cooling load or cooling coil will be applied and the room will be cooler. Okay, the supply air is technically T3 equals to T4 plus minus 20, right? T4 minus 20, usually because T4 is higher than the T3 lah, right? Okay. Now, there is not much calculation here. It's just some mental thought or mental experiment. Now, the condition was T1 is less than T4 or H1 is less than H4. So because the equation is given by this, and we all know this from thermodynamics class, Q cooling is equal to M air and the bracket H2 minus H3. Right, H2 minus H3. Okay, now it says here constant regarding the comfort of the conditioned space. So when we talk about H3 is always constant because the space is conditioned indefinitely. The space will always be conditioned where T3 is equals to T4 minus 20 or 75 Fahrenheit minus 20 Fahrenheit. Therefore, T3 is always 55 degrees Fahrenheit. Again, T3 is always 55 degrees Fahrenheit. Now, the mental thought goes this way. If you want to minimize the cooling load, we need to reduce H2. Alright, the bigger the H2, the bigger the Q cooling. That means if you have H2 is bigger than H3, right? So the number will be positive, right? The number will be positive and Q cooling will be bigger and become even bigger. If we can reduce H2 close to H3, then we will have some saving because economizer usually close the intake air and we want the room to be conditioned as cool as possible, right? So NH is given by enthalpy is sensible plus latent. So sensible is the temperature, latent is the moisture condition inside the room. So technically what we will have in our psychometric chart, if you still remember, a condition line from any state 1 to 2, but however to go there you will have a latent heat and you will have a sensible heat. Sensible heat and latent heat, right? Okay, so that is why in the psychometric chart you will have this graph, right? This graph. Okay, so this also the one that has a mixture is in this stage 1, 2, 4, right? 1, 2 and 4. So economizer is where you can mix the air that coming from the room. Let me go back up. Coming from the room there. So this 4, right, will go to here because this is closed already. This is closed, right? And then it will go to here and go to here. So economizer will open the OA or outdoor air a little bit, okay, little bit. So what we have here, there is a mixture there, the mixture between 1, 2 and 4. Let's go back to the picture. Where is 1, 2 and 4? Let me clear up, sorry, take eraser. 1, 2 and 4. So we have a mixture of like this, okay, right? 4 and 5 will be the same because they are in a similar line and 6 is close here, so we can assume that T4 is equals to T5 and you can just put T4 on the psychometric chart. So when there is a mixing, there should be a line, right? Maybe here is 1 and 4, in the middle here there is 2, where 2 is the mixing section. That is why you will see here there 1, 2, 4 in this line, okay, and 4 is equals to 5 and 2. Now 4 is not equals to 5 and 2 really. 4 is equals to 5 we take it 4 equals to 5. All right, now 3 and 4, right, the blue the green color, this one is our condition line. So let me write this down. Condition line. We want the room to be cold and maintain cold between state 3 to state 4. For each state 3 and state 4, you will have its own H enthalpy, right? Enthalpy. And also, this line, that green line there, will be parallel to the SHF. What is SHF? Sensible heat factor. Why do we use sensible heat factor? Because we have latent and sensible heat addition or rejection from this room. Okay, so this first diagram is for during, let's see back there, winter month, right? Winter month. Alright, so as you can see here, there's a outdoor air there. This is for T1, this is for T3, this one is for T4, right? Okay, T4. Now, H2 minus H3 will be here. So H2, the position of H2 or position of 2 is important because 1 and 4, when they mix, they will become 2. So if 2 gets this way, right, H will increase for 2. If, let's change the color, 2 drops close to 1 and therefore H2 will drop and become cooler, right? That means the air that goes into the room, right, it's number 2 there, will become either cooler or become hotter, right? So in winter, we want T2 becomes hotter, right? Becomes hotter. Alright, so during winter, 4, which is coming from the room, usually is hot, right? Because we heat up the room. And 1 will be cold, right? Cold up. Cold here, winter does not mean that the temperature outside should be 0 degrees Celsius. Sometimes, there's some countries, winter season, the temperature is more or less not that cold and then not that too cold. So let's say in the condition of winter is where the surrounding region is cold, right? It's cold. So therefore T1 is usually smaller than T4, like this, right? Smaller than T4. Alright, so if this is the case, we want the room to be warmer, so we close outdoor air, right? We close outdoor air, or we open it sometimes one at a time, and then we make sure there is an adiabatic mixing between line 1 and line 4, right? So there's a mixture. So we still want air to be coming in from outdoor air, right? Outdoor air, because we want fresh air to come in, but we make sure that there is adiabatic mixing. That means we close number 6, which is the exhaust. So what is it again? There, we close number 6, and we let 4 goes into 5 and mix with 1 and become 2, right? So 2 will become warmer, right? 2 will become warmer, right? So H, delta H, H2 minus H3, which we go back to this equation, right? To this equation, right, will become quite small. That means the cooling load will be smaller. Of course, in the winter, we don't really need cooling load. But the economizer will allow the mixture of adiabatic mixing between 4 and 1, and it become 2. And 2 is located along the line of 1, 4. As you can see here, right? As you can see here. Okay, that is the first situation of winter. Open the economizer, so we will have hot air mixed with a cool air, and the room will become or maintain temperature at 55 degrees Celsius all the time. Now during summer, usually T1 will become hotter than T4. T1 will become bigger. So we need to cool down the space indefinitely. Usually in summer, we will use a lot of energy to bring in cool air from outdoors when outdoor is very hot. So what we'll do is we need to make sure that T1 is bigger than T4, but H1 is lesser than H4. Then we will have saving. How to do this? To do this, we must make sure, if I can increase this, T1 is not that clear, yeah? T1, so this is the line, right? The line is maybe slightly like this, towards to the right. So that 1 and 4 with mixing, because we use economizer, is not really like this. In the winter section just now, it is slanted like this. So T1 and T4 looks something like this. So T1 is always more than T4, right? And 2 is here, T2. So with this, that means T1 is bigger than T2, is bigger than T4. So if you drag it to the line of H, you will find out that T1 or H1, right, H1 is less than H4. See, 1 is here, is still less than S4. But the line of saving, you can see here, compared to the winter section, is smaller. Therefore, we don't really have a lot of savings during winter, right? During winter. And usually, we must make sure that T1 is as close as T4, but not to overshoot, right? But not to be less than. This enthalpy, you must make sure H1 is less than H4. You can have T1 is bigger than T4, but H1 is bigger than H4 because outdoor air is very cold. Very hot, very hot, right? So what we'll do when the room is already cold, because using this as an aircon, we close line number 6. The cool air will mix with hot air number 1, so it will mix with number 2. So the room will become a bit warmer, but not that warm. But we must maintain this scenario. So even though T1 is bigger than T4, H1 is less than H4. If you look closely, right, so this is your T1 and T2 and T4. So we must make sure that H1 is less than H4. How do we do this? We open the economizer, close line number 6, cold air coming from the room, right, coming from the room will mix with the hot air that comes from outdoor air, right? So this is how we use economizer during winter and during summer. Let's go to question number 2. Question number 2, this tutorial, read, air at 40 degrees Fahrenheit or 5 degrees C, dry bulb, or 35 degrees Fahrenheit, 2 degrees C, wet bulb, is mixed with warm air at 100 Fahrenheit or 38 degrees C, dry bulb, and 77 degrees Fahrenheit, 25 degrees C, wet bulb. So there are two conditions, right? Okay, and then they are mixed together. One is cold and one is warm. So the ratio is 2000 cubic feet per meter of cool air to 1000 cubic feet per meter warm air. So technically, if I can draw this graph or a diagram like this lah. So 1, 2, 3. If this is 1, the cool air is 2000 CFM. So the warm one will be 1000 CFM. So it mix. Okay, it mix. MA1, MA2 equals to MA3. Find the resulting humidity ratio and enthalpy using psychrometric chart on the basis of volumetric flow rate. So you are not going to use the equation, but use the psychrometric chart. Alright, see the diagram for construction on chart 1A. 1A refers to the, I think is the English unit. Alright, so we will use this ratio, you see, 3 to 2 and a bar, 1 to 2 and a bar. So this bar refers to vector. Remember vector OA, right? An arrow there. That means the vector from A located towards the origin. If vector AB, that means OB minus OA, or from point A to point B, there's a magnitude of the movement from point A to point B with this vector. So it is the same. This bar is related to the vector. That means 3 to 2 is the distance between point 3 to 2, which is given by, so we can relate this with so many things, but in this case we can relate to CFM or cubic feet per minute. So the distance between 3 and 2, or from here 3 and 2, is 1000, right? 3 and 2 is Okay, so this is not 1 to 2, sorry. Okay, so let me draw this one more time. So I beg pardon. Okay, so we have 3 section. This is 1, this is 2, this is 3. So here it says cold air mixed with warm air in the ratio of 2000 cold air and 1000 warm air. So 1000 is for warm, 2000 is for cold, right? But there's a ratio to it. So ratio for cool air is 2000 and warm air is 1000. So if cool air is this one, right? So this is 2000, this is cool air. Sorry, cool air is here, 2000. Okay, just bear with me. This is 1000, right? So from 2 to 3 is 2000 CFM, right? 2 to 1 to 2000 CFM, and 1 to 3 is 1000 CFM. So this is a ratio. That means that goes from 0.2 to 0.3, that the 0.2 to 0.3, the CFM of cool air is 2000. From 0.1 to 0.3 is CFM 1000 for warm air, right? Warm air. So here it says 3000, 3 to 2 is 2000, like this, and 1 to 2, that means the whole bunch of this is 3000. That's true because 1000 plus 2000 is 3000. So we can cancel all of this. You will get Q1 equals divided by Q3 equals 2 to the power of 2 divided by 3. So with this psychrometric chart and this vector approximation, you can combine anything that you like. You can combine CFM like this, you can combine with heat as well. Alright, so the layout is 2L over 3. So we can bring this layout like this. It's quite small, right? Alright, so 3 to 2 is 2000. From here to here is 2000, and this is 1000, and all together from 1 to 2 is 3000, right? Okay, so 3000 because the length. Okay, so the distance, you can use ruler, right? Take a ruler. What is the distance? This is 2000 CFM, but what is in CM? From 1 to 2, 1 to 3, and 3 to 2. With this distance, you can do so many things, right? How many cm or how many mm, it depends on you, whatever you distance that you like. Okay, so these data are the enthalpy. So if it's 40 degrees Fahrenheit, it is 35 enthalpy, 54 is 52, and this is 100 Fahrenheit is 77 enthalpy, kg over kilogram. Or if in SI unit, will be in SI unit lah. Okay, so from here you can see that because you use a ruler, you can detect that W3 is 0.007. So this is your 3, right? So just use a ruler and plot it this way, right? So you got 0.007. Okay, so that is your relative humidity, and enthalpy is only given as 52. Okay, or I3, okay, there's another thing to talk about. Sometimes in thermodynamics, heat transfer analysis, they use I instead of H as well. Okay, so that 52 there belongs to the maybe SI unit, and 22.2 BTU or British thermal unit over pound of dry air will be the English unit. Okay, that's how you use psychrometric chart and a ruler to find the distance. So maybe, okay, you can see here one more time. We know that from 1 to 2, right? From 1 to 2, the ratio is 3000. Take a ruler and then find the distance between this long line. What is the distance between 1 to 2? And from there you can divide. Okay, divide the distance is ratio is 2/3, and find what is point number 3 just using your ruler. Okay, let's go to the next page. So the next page is I3. Well, in SI unit will be 33 kilojoule of kilogram of dry air, and omega will be that lah. Okay, now question 3. Rework problem 3 to 5, which is the one just now, using chart 1A with the mixture condition computed on the basis of mass flow rate rather than volume flow rate. So just now we used the volume flow rate, right? CFM. Now we use the MA or KGS, or pound air over hour for SR English unit, right? So layout is the same. So you can see that MA is 2000, which is TCFM, times 60, because we want to change from second, a minute to hour, alright, and then you divide by 12.66, which is the conversion to get pound, right? Pound. Alright, so MA2 1000 CFM times 60 divided by 14.44 equals to 4,155 pound of air divided by hour. Right, so this is the equation that you we see just now. MA is from 3 to 1, 3 to 2, right? MA plus M1 is the whole shenanigan from 0.1 to 0.2. Okay, so what you need to do is just to replace the values, right? And you get your answer is that. So that is your answer, 0.695. The ratio between 3,2 and 1,2. So the layout distance of 3,2 from on line from 1 to 2, we locate the point 3 of the mixture. So from there, right, because it's new, you can see there that 3 to 2 is 0.695, right? 695, and of course this is divided by 1. 1 will refer to 1, 2. 0.695 will refer to 3, 2. The distance, yeah, the ratio distance. And from there, you will get your I3, the new one, the new I3 as 21.5 BTU per pound of mass, and the humidity ratio is 0.0067 pound over pound, right? For W and for omega, that means the difference between the usage of volumetric flow rate compares to the mass flow rate, there is an error margin, right? For omega or W, there is around 4.5%, while for enthalpy, it is 3.3% difference, okay? So it depends on your condition. If you are more interested to study the volumetric flow rate, use it as much as you like. But the number is very small, 4% and 3% more or less. Okay? Alright. Now the final question sounds like this. A multi-zone air handler provides air to several zones. So you've learned about multi-zone already. One inter-zone contains computer equipment with only sensible load. That means a heat addition without water. The coil in the unit cools air from 85 degrees Fahrenheit and 29 degrees C dry bulb, 70 degrees Fahrenheit and 21 degrees C wet bulb, to 50 degrees Fahrenheit and 12 degrees C dry bulb. Relative humidity is 90%. If the zone to be maintained at 75 degrees Fahrenheit and 24 degrees C, right, and 50% RH, what is the portion of supply air to the zone bypass the coil? So this is using bypass. Remember the bypass from our lecture 5? So that is the one that we are talking about. The amount of air supplied to the zone is 2,500 CFM, cubic feet per minute, or 1.18 meter per second. That's for A. For B, what is the cooling load for the zone? Assume standard level, that means you can use psychrometric chart. Alright, so you have SI unit. We are using SI unit in this case. Now here on the basis of volume flow rate using chart 1B. So now we use volumetric flow rate. Volumetric flow rate, and therefore this Q dot again is not the heat. I know that you might be confused by now. If you talk about fluid mechanics engineers use Q as volumetric flow rate, but thermodynamics engineer use Q for heat transfer. Okay, in this case it is volumetric flow rate. The ratio is given by 1:3 and 1:2. So it is actually like this: Q2, Q3, 1:3, 1:2, and become like that. Yeah, so let's go to the graph. Okay, so point 1 and point 2 is where you take in where you have the condition of mixing, and 3 and 4 will be the condition that they want to maintain. So 4 is the maintain space. Usually maybe this is the equipment room that you want to maintain. Okay, so 1 to 2 and becomes 3, and it bypass. This is bypass. Alright, so maybe there's a mixture like this, and then there's a cooling load or cooling coil, but you bypass it like that. Okay, you bypass it. Alright, and then at this stage will be the mixture part. That's why you have a mixture diagram there. Okay, let's go to the answer. Okay, let's see, what do we get? 0.69. To get 0.69 is very interesting. So as you can see here, this, let me take another pen. So this 0.69 belongs to this ratio, and 1.1 is the volumetric flow rate, which refers to this. Okay, so what you need to do is locate point 1, point 2, and point 3 on the psychrometric chart. There. From there, find the distance between these long, right? So from 2 to 1 or 1 to 2, doesn't matter. And also find the distance between 2 to 3 and 3 to 1, right? And so from there, you can use the distance. So 1 to 3 and 1 to 2. So usually what we'll take is a portion, a smaller portion above, which is 1, 3, right? And the whole portion below. So this is the ratio of portion between the section and the whole section. Okay, so from there you'll see what is the distance in cm using your ruler for the whole line, and using your ruler for 1 and 3, and you get more or less 0.69. And this is the ratio of distance using the psychrometric chart, and we times that and you will get the answer is 0.815 meter cube per second for Q dot or for V dot. And therefore Q1 is equals to Q3 minus Q2 because it's a bypass, remember. So it is Q1 equals to 0.365 meter cube per second. Okay, so that is the bypass coil. Now number two is, what is the cooling load? Cooling load is Q equals to mCp delta T. Sometimes Q is equals to m delta H. Alright, now here you realize that if we use Q dot, a small Q dot, but here is a big Q dot, right? So this is purely fluid mechanics. In thermodynamics, this will be a big Q dot, which is Q heat transfer, and this will be big V dot. So what we do, what happens here, if you still remember your fluid mechanics and thermodynamics, m dot equals to V dot, which is the volumetric flow rate divided by specific volume. So I'm going to write here volumetric flow rate, mass flow rate, and this is specific volume. Right, so you get Q dot V dot V3 or small v, or the specific volume, from the psychrometric chart as well. Now Okay, Q dot is here, right? V dot, so V is what? Sorry, specific volume. Find it from psychometric chart. Where is it? Right, so this is state 3. So from there, use your psychometric chart, find the specific volume, and you will get your M. It's very simple. I3, I4, you will use your psychometric chart as well and find the numbers. Okay, find the numbers. So you will get the answer. Q from 3 to 4, the bypass section is 9.6 kilowatt. Right, 9.6 kilowatt, that is the amount of energy which is removed from that bypass to cool down that space. Okay, so these are very easy. What you do is you need a ruler, you need a psychometric chart, and just measure them using centimeters or millimeters. I think centimeters will be fine, just fine. Okay, and also use a protector, but in this case I don't have any question that have angles so for protector lah, so it's very simple. Maybe we can talk about SHF or sensible heat factor in another tutorial. And that concludes our week 8 tutorial, load calculation part 1. Right, it's very simple. I think just a little bit of new knowledge, but other than that, they're quite useful and quite easy, straightforward. Okay, so study well. Let's meet in our meeting. If you have any feedbacks or question, you can ask me in Telegram, and then I wish you good luck till the next video. Bye.